Hello, this video is going to show how we can achieve functional safety using Atmel Studio. Now, there are a couple of different boards that I could have used for this demonstration. I could have used an ATmega 2560 with either an external debugger or just an external programmer. But what I'm going to be using here is an ATsam E70, and this has an onboard debugger. Now, this is Atmel Studio, and I've loaded a project and I have the two files that I'm interested in. I also have all the framework that's been generated here, but I'm just interested in these two files. And let's check we can do a build. Okay, so that's already built. And what I'd like to be able to do is to first of all analyze this code and find out, well, is it good quality? What's the cyclomatic complexity of the functions? Is it compliant to MISRA? And then I'd like to be able to execute this main, and as it executes, I'd like to be able to find out, well, how much of the code have we actually exercised? And if we haven't got 100%, then I'd like to be able to use the unit testing tool tbrun in order to be able to complement that coverage. Now, let's put this to one side and let's perform a build here using the makefile. So in this particular case, we can see this is now performing the build, and it's building all this ASF framework. Well, as I mentioned, I'm not interested in that, but I need that to be built in order to be able to execute and get code off the target, because I'm going to be using a UART in order to be able to get the results off the target. So that's now built. Okay, let's now go into the LDRA launcher, and I'm going to start the build import. And in the build import, I'm going to run exactly the same build.bat that we just ran. But this time, LDRA is going to listen to what's happening, and as it listens, it's going to be able to find a list of all the source files. It's going to be able to find a list of all the defines, as well as all the necessary includes. So this is just going to take a little bit of time, but then when it's finished, we should be able to see the list of all the source files that have been found. Right, so there we can see we have an executable. We have 34 source files. I'm only interested in these last two here. These are the ones that I've written. We've also got a list of all the include paths, as well as all the necessary preprocessor symbols. So at this point, I could now go and open it with tbrun and then select just the two files that I'm interested in. But in order to save time, I've already done that, and as you can see, I've just selected these two files. Well, let's see if this code is compliant to maybe the MISRA C 2012 standard. And as we can see, there are quite a few violations. Well, let's take a look at one violation. Here we can see call as execution order dependent side effects. We have 4 instances of that. Well, let's click on one and see where that occurs. In this particular case, we can see we're calling this function roll dice 4 times. And we're expecting this one to be called first, then this one, and finally that one. But actually, what the C language says is the compiler is capable of executing these in any particular order it wants. And with some compilers, you might find it calls this one first, then this one, and then that one, in which case we'll get some different results. So fairly easy to restructure that bit of code. Okay, so now let's take a look at maybe a call graph. The call graph is going to give us a graphical representation of all the functions, and these are color coded to show these are functions we've excluded, and green to show effectively that the system calls. Now let's take a look at various metrics on the code. Maybe we can start by taking a look at metrics that give us an idea of maintainability, and then perhaps the most interesting is the cyclomatic complexity. Well, this is the most complex. It's got a value of 9. Well, let's take a look at that in a graphical view. So here we have a flow graph. We can see all the necessary blocks of code. So clicking on a particular block here, we can see the corresponding block in our graphic. We can also see we have a number of branches in the side of code. So in this particular case, this is a branch from here back to here. Now, what I'd like to be able to do is to execute this code and find out, well, how much of this code have we actually executed? So I'm going to put probes into the code. I'm going to instrument it and put a probe at the start and a probe at the end of every block, and then afterwards we'll be able to find out the coverage we've obtained. So to do that, let's go and run the dynamic analysis. This is going to first of all generate the instrumented code. Then it's going to use the same build mechanism, so it's calling the make to build all the files, and it's going to include the two instrumented files for the function files that I'm interested in here. So I should then end up with an executable, and it's then going to execute that on my target. So just waiting for that to finish the build. Okay, and now we can see it's actually starting to download to the target. So in this particular case, it needs to erase the flash, and then it's going to program it and execute. Now I need to get data off the target, and I could use the debugger to do that with a script, but what I've chosen to use in this particular case is to use a serial port. And so I've got a serial port connected, and I'm using TerraTerm in order to be able to capture what's happening. Well, that just executed, and we've captured the data using TerraTerm. We've now analysed that, and let's take a look and see, well, what coverage did we obtain? So once again, I'm going to a call graph, and this time I'm color coding it, so we can see in green the parts where we got full coverage, and in red the parts where we haven't got full coverage. So integer to ASCII, we've not got the full coverage. Well, let's see what we have actually covered. So once again, I'm going to a flow graph, and this time color coded in green to show us very clearly which paths we've taken through the code, and in red we can highlight the parts of the code we've not executed. Why haven't we executed this bit of code? Well, it looks like we've never had a value less than or equal to 180. Well, it's very easy to write a unit test in order to be able to try with that value and then get the full coverage. So let's do that. So let's go and invoke tbrun. So tbrun is a unit testing tool, and inside here I'm going to open a sequence of test cases that I've previously created for the integer to ASCII function, and I'm now going to execute these. So once again, it's in this case it's generated a harness, it's now building it, and then it's going to execute it again on the target. So while that's executing, let's take a look and see the sequence has got 7 test cases. If I click on each individual test case, we're going to be able to see the inputs and the expected outputs. Okay, that's now starting to execute on the target. Once again, it's doing the raising the flash, then it's going to program it, and we're going to capture the output with the TerraTerm. Okay, it's now started the TerraTerm, and it's now going to execute. We can see it's captured information via TerraTerm. We've analysed that, and most importantly, we can see that all these tests have passed. So with these inputs, we have got the expected outputs. And so now we can take a look at the coverage for this integer to ASCII function, and we can see we have 100% statement coverage, 100% branch decision coverage, and 100% MCDC. Okay, so hopefully that's given you an idea of how we can perform functional safety with the Atmel Studio. And if you'd like more information, then please don't hesitate to contact us at LDRA. Thank you.